The transition from dial-up to gigabit internet required a 4-decade engineering war against the laws of thermodynamics and material physics. In 1948, mathematician Claude Shannon defined the absolute speed limit for all telecommunications. This equation is the Shannon-Hartley theorem. Channel capacity, your maximum data speed, is governed by two physical variables, bandwidth and signal-to-noise ratio. To push more bits down a wire, engineers have two options: find more bandwidth or suppress the environmental noise. Every standard of broadband technology is a tactical maneuver to cheat this exact mathematical boundary over a different physical medium. The original public switched telephone network was architected for a single purpose: carrying the human voice. To route millions of calls across massive distances, telephone companies installed hardware filters at their central offices, restricting the copper line's frequency range to a controlled 4 kHz band. When the internet emerged, engineers had to force digital data through this narrow, noisy analog pipe using modems. By the late 1990s, dial-up modems peaked at 53.3 kilobits per second. Reaching this point meant engineers had mathematically maxed out the Shannon limit for a 4 kHz channel. To go any faster, telecommunications architects had to utilize the high-frequency spectrum previously ignored by voiceband hardware. Digital Subscriber Line, or DSL, bypassed the telephone company's filters to utilize the higher frequencies inherent in twisted pair copper. This allocation chart illustrates the shift. While voice traffic stayed below 4 kHz, early ADSL carved out new data blocks stretching from 25 kHz all the way up to 1.1 MHz. But the copper medium creates physical resistance. High-frequency electromagnetic waves suffer rapid attenuation, as the skin effect causes the signal to aggressively decay over distance. Additionally, because hundreds of these copper wires are packed tightly inside municipal cables, their electromagnetic fields leak into each other, creating crosstalk interference. This discrete multitone modulation graph shows how DSL slices the spectrum into hundreds of independent subchannels, evaluating the signal-to-noise ratio of each. The modem dynamically assigns data to clean frequencies, avoiding jagged notches where noise destroys the signal. This physical degradation meant the only way to reach gigabit speeds over copper was to shorten the wire. Engineers had to push optical fiber closer to the subscriber, shrinking the final copper run to a few hundred meters. Cable companies faced a different problem. Their hybrid fiber coaxial networks offered higher raw bandwidth, but their tree and branch architecture introduced a specific interference vulnerability. This schematic shows the downstream path broadcasting data from a central node to hundreds of HUNs. However, the upstream path acts as an antenna array, the noise funneling effect. Every loose connector bleeds ingress noise back into the line, compounding into a wall of interference. To push gigabit speeds through this pollution, the DOCSIS 3.1 standard utilized orthogonal frequency division multiplexing. Instead of using wide channels, OFDM divides the spectrum into thousands of micro subcarriers. It algorithmically targets frequencies hit by localized noise and applies intense forward error correction to keep the link stable. Modern multi-gigabit cable internet survives the Shannon limit through relentless, algorithmic noise cancellation in an environment that is physically polluted with radio frequency noise. To achieve even higher capacities, we must entirely abandon metallic conductors in favor of photons and pure silica glass. Inside a single-mode optical fiber, bandwidth expands into the multi-terahertz range. Attenuation drops to near zero, and electromagnetic crosstalk is physically impossible. In these passive optical networks, the main physical constraint is no longer electrical noise. It is the optical link budget, the precise insertion loss that occurs when light is physically split to serve an entire neighborhood. This optical strand cross-section demonstrates wavelength multiplexing. Because different frequencies of light don't interfere, multiple protocols can run simultaneously. A legacy GPON network and a 10 gigabit XGS PON network can occupy the exact same glass, simply by using different colors. Silica fiber removes the noise and attenuation constraints that define the Shannon-Hartley equation over metallic conductors, allowing network capacity to scale independently of geographic distance. Early broadband standards like ADSL and DOCSIS were architected with slow upload speeds to survive the physical line constraints of copper and coaxial cables. To deliver usable speeds under strict noise conditions, Network architects allocated the vast majority of the viable frequency spectrum to the downstream path, leaving only a tiny fraction for data leaving the home. Modern applications like Industry 4.0 and telepresence demand a network capable of continuous, real-time data creation. This schematic shows edge gateways pushing continuous robotic telemetry to the cloud, requiring massive upstream capacity. If routed through a restricted upload path, the data immediately bottlenecks. The resulting packet loss breaks the synchronization between the physical factory and its digital twin. This requirement forces the deployment of deep fiber architectures like XGS-PON. It provides the deterministic, symmetrical 10 gigabit throughput required to run global workflows without latency spikes. Broadband is the physical substrate of the modern economy. Our transition to symmetrical optical glass provides the necessary throughput for a landscape where physical distance no longer limits network capacity.